Okay, this problem says the blocks are moving to the right. There's a coefficient of kinetic friction of 0.01. The person's applying a 30 Newton force directed to the right. And can we find the normal forces between the blocks? First thing I would do is make all the blocks into a system. So our system becomes this entire blob. We need to know how much friction the system is going to feel. We know that there's a 30 Newton push, but we need to calculate how much friction is going to resist that push. It'll be kinetic friction because our blocks are in motion. So let's calculate the kinetic friction in this case. It'll have the formula mu k times the normal force. We're going to need to calculate how much normal force there is. So our blocks have a weight equal to mg, and we have to consider all the blocks. So we're going to add all the masses up to get the total mass of this system. Then we'll multiply by g. It's 90 kilograms total times 9.8. That makes 882 newtons. So our normal force will also be 882 newtons. It's just going to cancel the weight. Now that we know this, we could go on to find the amount of friction. Plug in the coefficient of friction in the 882 newtons. So our friction is going to be 8.82 newtons. Now that we know all the forces involved, we should be able to find the acceleration of this system using Newton's second law. Newton's second law says the sum of the forces here will equal m times a. So if we rearrange it, we'll get a equals F net over m. So our net force is going to be a combination of these two things. We'll do a subtraction, 30 minus 8.82, and then we'll divide by the total mass of the system. I get 0.235 meters per second squared. Now that we know the acceleration of the system, we could go on to find the individual normal forces between the blocks. So I would change my designation of system at this point. I would now make my system just one of the blocks, and usually the last block here is the easiest one to analyze. So let's figure out what are the forces on this block alone. So it's going to feel a push to the right, which is a normal force of block B on block C. I'm calling this one block A, block B, and block C. However, that's not the only force acting on C. There would also be some friction too. Fk. I'll call it Fkc because it's the friction that affects just block C. We can calculate that friction. Use the 0.01 coefficient, and then you need the mass of C times G to get his normal force. It's 1.47 newtons friction, and at that point we'd want to use Newton's second law for block C. So I'll say the sum of the forces on C will equal the mass of C times its acceleration. And so what are the forces acting on C? That would be these two forces. Now, of course, he's got a normal force and a weight as well, but they don't matter when it comes to the net because they cancel each other out. So we really only care about the x direction here. So there's an unknown push of B on C. We do know the friction amount, and we know C's mass is 15 kilograms, and we know its acceleration now too because we calculated it earlier. Plug in the friction amount. And now we can solve. So the force of B on C must be 5 newtons. So that answers one of the questions. Now we have to find the normal force of A on B. So in order to determine the force between these blocks, I would make a new designation of system. A is responsible for pushing both B and C. It's the only thing really in contact with them except for the ground. So we would treat this now as a system. And what I'll do is kind of pretend like the cut isn't there and make a free body diagram for the combination of B and C, which A is pushing. So there's going to be a normal force of A on B, which is part of the diagram. We're also going to have some significant friction involved, so we'll call that FKBC, kinetic friction on B and C together. We would have a weight for B and C and a normal force for B and C. So the weight will be the mass of B plus the mass of C times G. So that's going to be 50 plus 15 times 9.8, 637 newtons. So our normal force would also be 637 newtons. We can now find the friction. So let's do this. We have 6.37 newtons of friction acting here, and so that has to be taken into account when we do our Newton's second law. So we'll say the net force on B and C is equal to the mass of B and C times the acceleration of them. Now, when you do a net force here, you have to take into account both of these forces. So on the left-hand side, I'll show that there's a push of A on B. We're going to subtract the friction and let that equal to the mass times the acceleration. We've already determined that the friction is 6.37 newtons. So let's put that in, and our mass of B and C will be 50 plus 15. Our acceleration was earlier found to be 0.235. It's 21.6 newtons. So, what we've found is that we have 5 newtons of force between these surfaces, and we have 21.6 newtons between those surfaces. The force between the hands and the block is, of course, 30 newtons, the original push. And it should always be like that, where you start with a high value at the point of contact, and then the value goes down as you move through the object, because at this point, you only have to accelerate this much of the mass, or this portion of the mass. When you get to here, you only have to accelerate a smaller portion of the mass. So the normal force is going to be proportional to the amount of mass that has to be accelerated. Now, interestingly, if I compare these numbers to what I found in a previous problem, the previous problem was supposed to be one where there was no friction. But interestingly, the values ended up being the same. So 30 newtons applied here, 21.6 will be transmitted to this point, and 5 newtons transmitted to this point. But the main difference between the two problems is that here we have a higher acceleration as a result of those 30 newtons of push, because there's no friction resisting the push. Down here, the person applies 30 newtons again, but we see that the acceleration is much smaller because friction is acting against the push.